Good evening, everyone. I'm Jim Kekelius, the head of the School of Physics and Astronomy, and I want to welcome you to your University of Minnesota. We have a summer of astounding astrophysics. This talk actually is going to address how it started and how it's going. On behalf of the school and the Minnesota Institute for Astrophysics and the Fine Theoretical Physics Institute, I want to welcome you to the final talk of our session of a summer of astounding astrophysics. Today's talk is by Professor Keith Olive, who is the Gloria Becker-Lumpkin Chair in Theoretical Physics in the William I. Fine Theoretical Physics Institute, and he's also a member of MIFA, the Minnesota Institute for Astrophysics. He received all of his degrees from the University of Chicago and joined Minnesota in 1985. In addition to receiving the George A. Taylor Research Award from the College of Science and Engineering and the Distinguished McKnight University Professorship, he received from the American Physical Society in 2018 the Hans A. Bethe Prize. Now, this is a prize given to one scientist once a year to recognize outstanding work in theory, experiment, or observations in the areas of astrophysics, nuclear astrophysics, or closely related fields. And Professor Olive's award was given in recognition for outstanding contributions across a broad spectrum of fields, including nuclear physics, particle physics, theoretical and observational astrophysics, and cosmology, especially Big Bang nucleosynthesis and the properties of dark matter. And everything that he's going to talk about today can fit on a t-shirt. And I say that because I have the t-shirt. And this t-shirt reads, "The universe exploded out of nothingness 14 billion years ago. And all I got was 100 trillion interconnected cells, a self-aware consciousness, and this lousy t-shirt." So I do this, and how do I maximize? What do I do there? Oh, it's up on top. Okay, very good. And now I hand it over to Professor Olive.
Okay. Thanks, Jim. I'm really sort of amazed or astounded that so many of you have come out to hear all the crazy things I'm going to tell you in the next hour. No, really, it's nice to see that there's so much interest in the field. So tonight's talk will be on the early universe, on Big Bang theory. And so we're going to concentrate on the very earliest moments and what I'm going to tell you about what we know about the universe at those earlier moments and how we go from those moments to the present day. And so the subject as a whole is cosmology. So that's the science of cosmology, is how we describe the universe. And to do that, I'll have to tell you at some point something about the fundamental forces in nature and particles in the universe and how those particles interact with those fundamental forces. As I said, I'm going to concentrate essentially on the first 3 minutes of the universe. Jim said the universe is 14 billion years. That's pretty close. It's about 13.8 billion years old. But we're going to be focusing mostly on those first 3 minutes. So the big picture, big scope, as I said, the universe, we have it pretty accurate to be 13.8 billion years old. The G is giga. It's for billions of years, billion years old. The universe is expanding, and we'll go through what that means and how we know that it's expanding. That expansion is actually accelerating. That is, the universe is expanding, but it's expanding faster and faster as time goes on. That's something that's relatively new in the last 20 years or so, 20, 30 years, that we've appreciated that. I think before that, really the expectation was the universe is expanding, but it's slowing down and slowing down. But now it appears really the universe that expansion is accelerating. and that'll have very profound consequences. On the big scales, the universe is homogeneous and isotropic, and I'll tell you a little bit more about what that means. But basically, on very large scales, the universe is very smooth, and it looks the same in all directions. So that's what those two things are referring to. So how did the universe start out? Again, just very broadly, the universe seems to have come from some very, very hot and dense state, and it was initially filled with radiation. Now, when I say radiation, what we mean by radiation is just very high energy particles, not really in the sense of radiation as being something dangerous or medical or nuclear. It's just that there was so much energy around that all the particles were moving essentially at the speed of light, and we term that as radiation. As I said, the universe is expanding, and as it expands, it cools. So it started out very, very hot, in fact, much hotter than even the center of the sun, but it expands and it cools. And eventually we get to the point where you start forming the first nuclei, and then eventually you form neutral atoms, and eventually you then get to forming stars and galaxies. But also what happened very, very early on, that there were some fluctuations that were present. And those are the things that eventually grew into what we see now as galaxies or clusters of galaxies. And these are now dominated by dark matter. I'm going to say a little bit about dark matter towards the end of the talk, but that's not what the focus tonight is. It's a big part of our universe today, but it's not. It wasn't as important in the very first moments. And the accelerated expansion is very late. So well, actually, there were two periods of accelerated expansion. There was one very early on, which I will talk about. And then it appears now we're again going into this phase of accelerated expansion. And that's dominated by something that we term as dark energy. And I'll say a little bit more about that later. So I thought to start with, we just can relax a little bit, look at some pretty pictures. First of all, they give you some sort of scope as to the size of the universe and how deep the universe is. And also, they always amaze me because these are all fairly recent. This is a picture taken by the James Webb Space Telescope. And detail there is really amazing. Most of what you see there are not stars. They're all galaxies, individual galaxies out in space. The thing that looks like a question mark is actually a composite of a galaxy. I'll say a little bit more about that later. It's about 5 billion light years away. So just to give you a sense of how far and how distant these things are. This is a picture of the sky taken from it's composite of two satellite sets of data, one from the Planck satellite, the other one from the Gaia satellite. What you're seeing in the center, the strip in the center, is just our galaxy. So these are what are called galactic coordinates. So the galaxy is taking the center of this plane, and then the rest of the sky is projected about that. The white is all the light coming from our galaxy, and in the center, and then you have all the white coming out all around it is mainly obscuration from dust. In the corner here, there's a little corner, there was a patch. So this was studied and released, I think 6-7 months ago by the Euclid telescope. And so they looked at a little patch of the sky. So this is that same patch that I showed you before. And on the sky, the size of this patch is, you can see here, the size of the moon relative to the size of that patch. And what I find so neat about this is that, they were able, the resolution is so great that they're able to zoom in, you see, up to like 600 times, and we'll see what we see from that. So at 3 times the projection, you get a picture that looks like this, that looks interesting. Again, most of the things there are galaxies in the background. And now at 12 times, you see a few things. You have here a galaxy. This one's about 25 million light years away. And here you have this line here is a cluster of galaxies. And that one is about 700 million light years away. Not quite like the other one, but still very, very distant. Here's a zoom in on that. So here's that line. This is a cluster of galaxies here. That's the one that's 700 million light years away. You have here a pair of galaxies which are interacting with each other. they're about 400 million light years away. You can zoom in again on those two. So here are these two galaxies at 400 million light years. And you think about the light coming from that was emitted 400 million years ago, and you see it with this kind of detail, and they could zoom in even more and see that galaxy. This is to me, is really a phenomenal picture. So the technology that goes into these telescopes now is really amazing. So this is a picture of sort of schematic of the history of the universe that is often shown, particularly by people doing cosmology and astrophysics. What you have here is starting with this, there's a disk here, and I'll talk more about this disk. This is what's called the surface of last scattering. This is where the light that filled the universe last scattered. So at times later than this, that light just freely streamed out through the universe, never hits anything anymore, and that's what we eventually see. And this is called the microwave background, and I will tell you about that as we go along. And then you have everything else. There's a little period here, which is called the dark ages, because basically everything was dark. There were no stars, there were no galaxies, there was just nothing. It took a little bit of time. This is at about 300,000 years after the Big Bang, and then this is about a few hundred million years after the Big Bang. So there's a little gap in time where there's nothing, and then eventually you have stars forming and galaxies forming, and eventually you get up to today. What I'm going to talk to you about today is everything to the left of this disk here, okay? So I don't want to show you that picture. I'm going to show you, this is not quite as fancy and nice, but there's a real lot of information in this picture. And so this is the picture that we're really going to be talking about. There's a time scale here, and that time scale is in seconds or years as you go down to the right. We start at ridiculously small times, 10 to the minus 36 seconds. I'll tell you a little bit more about that time scale. You have the Big Bang here very early on, and then you have the microwave background is being formed. This is the period where the universe is extremely hot. The universe is expanding. This is that period of accelerated expansion that I mentioned early on. And then the universe goes through a various sets of things that we'll be talking about that are going on. The formation of the light elements, and then eventually getting out to the cosmic microwave background here. The second line is telling you something about the temperature of the universe in units of Kelvin. So Kelvin is the unit for absolute zero. 0 degrees Celsius, for example, is 273 degrees Kelvin. When you get up to the higher temperatures here, the unit actually doesn't matter whether you're using Kelvin or Celsius. It's all the same. But you see, we're here today at a temperature of about 3 degrees Kelvin. So that's what the temperature of the universe is now, extremely cold. And as you go back, you see the temperature of the universe. The 10 to the 9 is about the temperature at the center of the sun. And we're going to be talking about temperatures significantly higher than that, out to 10 to the 28, 10 to the 32 degrees. Okay, so that's how hot the universe started. Orders and orders of magnitude hotter than the center of the sun. The third line is the energy, typical energy that a particle would have. And this is in units of GeV, so G again, giga, so 10 to the 9, a billion, electron volts. And the electron volt is a unit of energy. You can think of it as if you have two plates and you put a voltage of 1 volt between the two plates, and you put an electron on one plate and it accelerates to the other plate, you get 1 electron volt, and this is a billion electron volts. And so here are the typical energies that are going on in the universe. So when you get to about 1 GeV, that energy is like the same energy as the mass of a proton. If you convert the entire mass of the proton into energy, you get 1 GeV. So that's about here. But we're going up to much higher energies, 10 to the 15, 10 to the 19 GeV. And at some point, our understanding breaks down and we can't really go beyond that. You're probably even wondering, how do you even know you can go to that plate? And that's a little bit of what I'm going to try and convince you about, that yeah, there are mechanisms and there are ways that we can understand and probe the universe at those really early times. So to understand the universe, we need to have some understanding of gravity. And for the most part, Newtonian gravity works really well. If you're talking about projectiles or satellites or planets, all of that Newtonian gravity works really well. But it is just an approximation. And if you want to study something either more massive or much larger, you need to go beyond Newtonian gravity and the theory that a better theory of gravity, a more complete theory of gravity, is general relativity, which was developed by Einstein a little over 100 years ago. And general relativity is a theory of curved space-time. Okay, so there's a lot in that one phrase, because thinking about space and what does it mean to curve space, let alone space-time, and what does it mean to curve space-time. So I'm going to have to take a few minutes to try and get that concept over to you so that, that we can go on. So space appears flat. You probably never even gave it another thought that space is not flat. For all intents and purposes, it seems quite flat. But instead of starting with space, let's start with a much simpler case of that of a circle. So the circle is a one-dimensional object. So when I talk about the circle, I'm going to say you have to be on the circle. You can only go around the circle. You can't go off the circle. You can't go inside. You can't go outside. That's not part of your world. It's not part of your space. So if you're small compared to that circle, it'll look flat. So let's just look at a little segment of that circle, little arc. So it's still an arc. It's still a little bit curved there. It looks curved. But if I pull it out, it'll look flat. So the smaller and smaller piece of that circle that I look at, it looks flatter and flatter, right? That's why the Earth looks flat to us, because we're such a small piece of the entire Earth. When we look out, it looks flat. The ocean looks flat, but we know it's not. So there are two ways to find out that this is not flat and that it is curved. One is to move off of it, right? So if you can get off the circle and move out into the plane, you see, I put the circle here on a plane. In fact, whenever you think about the circle, you're always putting it on a plane, because it's very hard in the abstract sense to think of just the 1D circle without the plane there. So if you move off the plane, then if you move far away from the circle, you can see, oh, I can see the whole circle. It looks round, right? Or I can go around the circle. If I can sample large distances on the circle, I can find out, oh, if I keep going, I'll come back to where I started from. And I'll say, okay, that's some sign of curvature. So I've been lying to you a little bit, because the circle is not a real great example, because there are no curved one-dimensional spaces. So if I cut this thing, I can just spread it out and it'll look flat. So that was a bad example. But we go to the next one, which is not a bad example. And that's the sphere. So let's go to a two-dimensional space. So now we can use the Earth as the example. So the Earth, this one really is curved. And you actually know it. You can even think about why I'm saying that, because if I think of a basketball or anything, if I cut it, right, I can't flatten it out to a plane. You can imagine I take that ball and there's always going to be something that's sticking up. It won't go perfectly flat everywhere. And that's a signature of the fact that it's actually curved. Now, again, like the circle, I'm going to say you have to be on the surface of the sphere. You can't move off. You're stuck to it. You can't move in. You can't move off. And because of that, again, if you're looking at sampling very small portions of that sphere, it will look flat, which is what I said before. The Earth looks flat. And people for hundreds or thousands of years thought the Earth was flat. But if you can move off of it, like go out into space, then you can see that the Earth is not flat. Or if you can sample large distances, like Magellan, you can sail around the world and find that you come back to where you started, and therefore it has to be curved. Okay. So straight lines in curved space, they're also a little bit funny once you get to non-flat spaces. So if you've done this, I've done this many times, and not even that long ago, fly from Minneapolis to Paris, you'll find that the airplane takes this kind of a path, and yet that's a straight line. You might think, or if you've flown it, you know that's not true, that that would be a better path for the plane to take. But that's because we've done this funny projection, which again, you can see there's something going on because Greenland is like really big up there. And that's a sign of the projection. So on the sphere, the plane really is taking the straight line. And these are the great circles. And so again, the fact that the Earth is curved, that the sphere is curved, what we think of as straight lines really depends on how we do the projection. So the plane really is taking that straight line. So what about three space, the full three-dimensional space that we live in? How do we describe that as being curved? So now we have the problem is we can't step outside of it. I can't even draw it, right? So the sphere I can draw because you can do some tricks with, you know, making something that's two-dimensional look three-dimensional, but I can't do that with a three-dimensional thing because I have to put it in a fourth spatial dimension, and our brains aren't wired to conceive of four spatial dimensions. So we can't step outside because we don't even know what that means. So all we can do is sample the large distances. If we want to see that the space is curved, we have to sample large distances. This was one of the tests of Einstein's theory that he actually went out and did himself, is to look at the bending of light around the sun at the time of an eclipse. So the stars, if you have background stars, astronomers know very well where they are at all times. And so you can look at a star, so behind the sun, that's why you need the eclipse, because otherwise you wouldn't see anything, but you can look at a star that's actually behind the sun, and the light will be bent by the gravity of the sun, and our minds and our eyes tell us that the star is here because we think that the light is coming to us in a straight line, what we think is a straight line. But this is a little bit of an exaggeration here because you see this is 1.75 seconds of arc. It's a very small deviation, not like what's shown here. But this is where the star is actually present. So the fact that you can see the star here and you know that the star is here, you can measure this deflection, and that deflection is what was predicted by Einstein's theory. So, and that proves that the presence of the sun, the gravity of the sun is curving the space because this is actually the straight line, like on the Earth. Now, you can do that, you can probe things much deeper. So you can set up sort of an astronomical optical bench here. So we're here, and we're looking at some really distant galaxy back here. But we pick one that's sitting right behind a cluster of galaxies. And then what's happening is that the light coming from that galaxy is coming around and getting bent by this cluster, and it's going around the other way. And so we're seeing this galaxy in all different directions. In fact, there will be like a ring. This galaxy will get spread out into a ring. We'll see it in that way. Does this actually happen? Well, here's a picture that was taken, it was probably about 30 years ago now. You can see here, there's a blue galaxy here. So the thing in front here is the cluster of galaxies. To me, it's green, but green or yellow light here. And then there's the blue galaxy behind, but you see there's another one here, and there's another one here, there's another one here. Those aren't different galaxies. Those are all exactly the same galaxy being lensed by the cluster of galaxy that's sitting in front. So the gravity here is bending the space so that the light coming from this galaxy is getting deflected and appears to form this kind of a ring. Here's an even more dramatic example. This is one galaxy just getting, the light getting deformed. This particular galaxy is about 5 billion light years. The lens here, the cluster of galaxies in front, is 5 billion light years away. The galaxy itself is about 19 billion light years away. And I'm going to have to make you think about that for a moment, because I told you, and Jim told you, that the universe is only 14 billion years old, 13.8 billion years old. So how could this galaxy be 19 billion light years away? Not going to tell you now, but if you're interested, I'll tell you later. Here's another great image. So here you see again gravitational lensing, so evidence that the space is curved. So again, the one galaxy getting deformed. This one is really special because you see there are 3 dots here. Those 3 dots are supernova explosions. So that's a single star in this galaxy exploding. This is actually the same supernova. It's not 3 different supernovas. It's the same supernova being lensed. And what you're seeing it is at different times as well. So you can study the evolution of the supernova explosions. And Pat Kelly here at the Minnesota Institute for Astrophysics is really an expert on that. All right, homogeneity and isotropy. So I already said that on large scales, the universe appears to be homogeneous. Okay. We know it's not true if you go to smaller scales because we have stars, we have planets, we have galaxies, we have clusters of galaxies. All that is very lumpy. The density inside a galaxy is orders of magnitude larger than the density of matter outside the galaxy in space. So there are big variations in the density, but if we average it on very, very large scales, then it appears to be smooth. There is an average density that does fill up all of space. And the isotropy is basically telling us if we look in any direction in the universe, it looks more or less the same. It's not going to be exactly the same, and I'll tell you about that in a short while. But those two attributes of the universe are extremely important. Oh, actually, so here's I'm going to tell you right now how the degree of lack of isotropy or inhomogeneity there really is. This is, again, this map. This is that same disk I showed you on that one slide earlier. This is what's the microwave background, and I'll tell you more about the microwave background. But this is the light in the sky. This is the light that's at 3 degrees Kelvin. This is the temperature of the universe across the sky. Again, same kind of map here. The galaxy is in the center here. It's been taken out so you can see the microwave background over the full sky. The different colors here are little temperature variations. So it's 3 degrees everywhere, 2.7 degrees everywhere. But you see with variations of a few hundred microkelvin. Okay, that's how smooth it is. That basically overall the sky is 3 degrees, but some places it might be 300 microkelvin hotter, some places 300 microkelvin cooler. And that's the difference between these red and blue patches here. So there are consequences to homogeneity and isotropy. One is a practical one for somebody working in the field. It makes it a whole lot easier to do any kind of calculation if the universe is homogeneous and isotropic. Basically, the problem is almost unsolvable if we had, sort of a crazy composition for the universe. Doesn't mean it wouldn't exist, but it would be very hard to do any calculations. So it's very convenient for a theorist that the universe is homogeneous and isotropic. So what are the consequences? One is that there are 2 possibilities. One is that the universe is sitting still. And so it's called the Einstein static universe. And it's called that because Einstein, despite the evidence was really available to him, he wasn't aware of it, he found that the universe was either expanding or contracting in his models. You can call them his models because he invented it. And he didn't like it. He didn't like it. So he wanted to stop that expansion. And he found that there was a way to do that by adding a constant, this what's called a cosmological constant. And the reason he found that you can do that, there's a very simple way of understanding that, is that Einstein's equations they're differential equations. So to get the solution, you have to integrate them, if you remember a little bit about your calculus. And when you do an integral, there's always a constant of integration that comes out. It doesn't affect anything because then when you take a derivative, that constant goes away, but it's always there. He found that if he adds that constant, it doesn't affect his solutions other than it can cancel the expansion. So he was able to get a static universe. And then he was very embarrassed by the fact that when it became known, principally then by Hubble's work, that the universe was in fact expanding, he thought that was a huge mistake he made, but we'll see that that was not such a mistake maybe after all. But given that it's not static, the universe will either expand or it could contract, although we happen to be living in an expanding universe. And that then gives us Hubble's law, which just tells us that the velocity of a distant object, like a galaxy, will be proportional to the distance, and that constant of proportionality is called the Hubble constant. So here's what that looks like. There's a nice linear relationship. This is the distance to an object that you're looking at. In the units here are megaparsecs, so millions of parsecs. A parsec is an astronomical unit that's about 3 light years. So megaparsec is about 300 million light years. So these are galaxies, distant galaxies. And here's the velocity, and the velocity here, if you can read it, it's in kilometers per second. And so we're talking about velocities which are 10,000 kilometers per second. That's sort of a crazy velocity to be thinking about, that something's moving 10,000 kilometers every second. That's how fast these galaxies are moving away from us. And so does that tell us that, that the universe is expanding? But what does it mean that the universe is expanding? So flat space, the universe could be flat. I say it's curved, but it can be curved, it can be flat. It's actually pretty flat, as the experiments seem to be telling us. But even if it's flat, and even if it's infinite, so there's another concept you have to grapple with, that the universe might be infinite, that it goes out forever, it could still be expanding. And the thing about the expansion is, so everything is moving apart from each other, but not relative to the space. It's the space itself that's expanding. So how does that work? So we can look at like this Go board with some Go chips here, and you put a few chips there, and those will represent galaxies, and they're on certain coordinates there. And so this is a plane. So I'm not doing it in 3 space here. I'm thinking of a plane, an infinite plane, right? It's in this case, it's flat. There's no center because it's an infinite plane. There's no place on there that you would call the center of the plane. And it's expanding. So if I go to a later time, it'll look like this. It's still infinite, but everything's farther apart. But the chips are still at their same positions, but they're all their distances between each other are all farther apart. And they're all moving away from each other. No matter which chip you're on, all the other ones are moving away from you. Okay? There's no center. You could have a closed space. So in that case, maybe the volume is finite. And it's still growing, so that would be like the picture on a sphere. So again, doing a 2-dimensional analog of the 3-dimensional space, you would put your chips on certain longitude and latitude lines, and you blow up the sphere, and all the points are moving away from each other. Now, the common question is, well, what's it expanding into, right? Well, nothing. Because remember, if the universe is infinite, it's already all there. Even if it's finite, you can't talk about anything off the sphere, right? Because now we're talking about 3 space. It's the 3 space that's getting bigger. Even if it's curved, you can imagine in a 3 space, you go out in a rocket ship for a long time, and then you come back to the other side. Or you can shine a light at the back of your head and wait for the signal to come and see the back of your head that way. The only problem is it actually takes the entire age of the universe for that to happen. That's detail. So Hubble, actually, his work, he got the wrong number. So his Hubble constant was about 500 kilometers per second per megaparsec. You say that's a funny unit, but how you interpret that unit is if you put a galaxy at 1 megaparsec, it will be moving away from you at 500 kilometers per second. So it just tells you the velocity. This constant actually is related to the age of the universe, and this would predict the age of the universe to be about 1 to 2 billion years, which is a little bit of an embarrassment because the solar system is about 4.5 billion years. So that doesn't work out. So it's okay. You know, there's some inconsistencies. Not everything works exactly right in the beginning. They're led to competing theories. And for a long time, the 2 main competing theories were called the Big Bang theory and the steady state theory. So the Big Bang theory was originated by George Gamow and his collaborators, and steady state was by Fred Hoyle and his collaborators. It's actually Fred Hoyle who named the Big Bang Theory the Big Bang Theory. It was in a radio interview. He was actually trying to put down Gamow's theory, and he thought if he called it the Big Bang Theory, it would sound silly and nobody would take it seriously. Whereas the steady state theory, that sounds like a real scientific thing. But it doesn't work that way, because eventually you have to do an experiment, right? Physics is about making a theory, doing an experiment, it's right or wrong, right? And the steady state theory was actually falsified. So the Big Bang Theory predicts a 3-degree microwave background, which I've alluded to a few times. It also predicts the abundances of light elements. But it was the 3-degree background, and I'll talk more about this, that really killed it, because there is no 3-degree background in the steady state universe. Steady state universe is basically the universe always looks the same at all times. So it's expanding, but in the gaps, there's new matter that's created and making new galaxies. And so on average, it always looks the same. Whereas in the Big Bang Theory, it's changing dramatically over time. Not so much in our lifetimes, but over a period of time. All right, now we can go back to this picture and talk about what actually happened at the very early times. So this time, this 10 to the minus 36 seconds, really is sort of embarrassingly early. It's really hard to even fathom what this kind of time scale is. I mean, you've all heard about nanoscience, and so a nanosecond is 10 to the minus 9 seconds, okay? And then recently, 10 to the minus 18 seconds became news, because that's sort of the light travel time on atomic scales, and there was a lot of new work being recognized with experiments on this kind of time scale. But this is 18 orders of magnitude smaller than that. So it's really a sort of a crazy time scale. So what happens at t equals to 0? Well, you notice, and as I got to apologize, there's a question mark here. I don't know, right? Nobody knows what happened here, right? And the big problem is, again, you don't have a theory of gravity that's a quantum theory of gravity. We'll talk more about that. So at t equals to 0, the Big Bang Theory or classical general relativity would tell you that the volume of space goes to 0, the density goes to infinity, and gravity gets strong, and that's why you need a quantum theory. Okay, and we just don't have it. Maybe it's string theory, but that hasn't been tested. It's very hard to test this because general relativity is anyway a big challenge. That's a correction to the Newtonian gravity, and string theory would be a correction to Einstein's gravity, and so it's really hard to test it. So now we come to the fundamental forces, and there are 4 of them. I know you're counting 5, but there's 4 of them. Electricity and magnetism have been known since the 1800s really to be the same thing, just different manifestations of the same thing. And that was largely shown by Maxwell. Our understanding of electrodynamics with quantum theory is largely due to Feynman's work. The weak force, so that's in simple terms, is what governs radioactivity, the fission processes, the breakup of nuclei. And that was done in the 30s by Fermi and others, of course. And that's now been unified, or in the 1960s, led by Steven Weinberg, our understanding that even the weak theory and the electromagnetic theory are really sort of connected. And this is an incredibly well-tested theory now. This is what's been going on at CERN, at the LHC, for the last 10 years or so, even more than that. It's actually disappointing how well this theory works, because you'd always like to see some breakdown of the theory so that you can learn something new. But this theory is very, very well understood and very, very well tested at high precision. I think it amazes everybody in the field that it seems something we got right. The strong force is what's related to nuclear binding. So that's what keeps nuclei together, or fusion processes. And there were attempts in the 70s to combine that with the electroweak force. It's called a grand unified theory, or GUTS. Should have worn my t-shirt. I have a t-shirt that's Cosmology Takes Guts. And eventually you would like to get some theory which unifies with gravity. And as I say, the only thing we have now is string theory for that. So what are the types of expansions that you can have? Well, depending on what's dominating the matter of the universe, what's dominating the universe will determine how the universe is expanding. If it's radiation, again, high energy particles, goes as a power law, T to the 1/2. Okay, nice gradual expansion of the universe. If it's matter dominated, it's more or less the same thing, different power. You probably don't care. If it's vacuum dominated, it goes very different. It goes as an exponential. It starts zipping out. But now you're thinking, what does he mean? Vacuum dominated. Vacuum, there's nothing there. So how can it dominate over anything? Right? So what you think of the vacuum and what I think of the vacuum might be two different things. Right? So vacuum is a state of nature that determines the properties of the particles you put in it. So I can have two different vacua. Right? I know there's nothing in there. There's no matter there. But if I put matter in one vacuum relative to putting matter in another vacuum, they might behave very differently. Okay? And you can be dominated by the vacua if one vacua has more energy than the other. Okay? That's, again, a little bit tough to grasp. And I'm going to show you a picture which might even be tougher to grasp. This is, I always dread having to show this, but I sort of have to. This is a picture of vacuum, vacuum energy or vacuum energy density here. And this is some parameter that describes which vacuum you're in. We don't, it's just, there's two different states. One is here, one is here. And I'm pointing to the minima of these because those minima are telling you that, well, the universe always wants to be a minimum, lowest energy state possible, right? You're all sitting, you're not standing here, right? So lower energy state, you want to be sitting during this talk. So this is the grand unified vacuum, and this is where we live today. And there's an energy difference. And you see that it's temperature dependent, okay, and there's a little barrier here. So classically, if the universe got trapped in this vacuum, and what I mean is that if I put a particle in this vacuum, that is the state of the vacuum is here at 0. The properties like an electron, if I put an electron here, it won't have any mass. So protons wouldn't exist. Whereas if I put the electron here, it will have mass, protons will be present, and they will interact in the ways that we know them, right? Here we know how they interact as well, but they're not what we see in nature. This is the unified theory. This is where we live today. But quantum mechanically, you can go from one to the other. And that happens through what's called a phase transition, and that happens through what's called bubble formation. And you can ask, what is now what is he talking about? Bubble formation in the vacuum. So these are vacuum bubbles. There's nothing in the bubble, there's nothing outside the bubble. All right. But there's energy in the wall of the bubble. And what I even mean by bubbles? Well, you know what I mean by bubbles because you've all witnessed first order phase transitions in your kitchen by boiling water, right? You're turning liquid into steam, and that happens through the formation of the bubbles. Now, when you're doing it on the stove, those bubbles form at the edges of the pot, but that's because there's edges of the pot. If you had a really big volume of water and you were able to heat it uniformly, then the bubbles would form randomly inside the liquid, and they would be bubbles with steam inside. So you have liquid on the outside, steam on the inside, and eventually those bubbles grow and they all merge and the whole thing turns to steam if you get it hot enough. The same thing. You got this unified theory bubble on the inside, and then you have outside, you have the other way around. The standard model, where we live on the inside of the bubble, they all have to merge, and then you go forward. That's the basis of this theory called inflation, which took place at around 10 to the minus 36 seconds. And that was developed in 1982 or so. There were some works before that led to that. And that one of the reasons that that became so useful is it helps determine whether the universe is open or closed, or this parameter omega, which is just a way of characterizing how much matter there is in the universe relative to critical density. So critical density just is distinguishing between the open universe or the closed universe. And so either the one that's infinite or the one that's maybe finite in just very simple terms. And it seems this parameter is extremely close to 1 very early on, and nobody knew why. And so there are all sorts of different explanations. One is called the anthropic principle. It says basically that if omega were different than much different than 1, there would not be any human life to ask the question. So you don't care. So as soon as life is there, it had only come when this value of this parameter was about 1, where the universe was almost perfectly flat. Yeah, you know, it's hard to disprove, right? Because you can't repeat it. You can't do another universe where omega is 10 and find, oh, there's nobody there, right? So we only have one universe, and it's about 1. It's very close to 1. And that argument works. It's easily discarded as soon as you find another reason, and inflation is one reason that tells you that the universe is very flat. It's a very simple explanation because this exponential expansion of the universe, dominated by the vacuum, blows up the universe to be so big it appears to be flat, right? Just like we said that us compared to the surface of the Earth appears flat. The universe will appear to be flat if you make it big enough. It also explains why the universe is so isotropic and homogeneous and why the temperature is 3 degrees everywhere. But Alan Guth really developed the theory originally to explain the absence of what are called magnetic monopoles. And you might say, again, what is he talking about magnetic monopoles? Because well, all of the magnets that you have, every single one of them, has a north and a south pole. I sort of tempt you to go to your hardware store and ask the salesperson there, can I have a bag, a dozen North Poles? And see the expression on his or her face. Well, in the theory, you could have North Poles and South Poles as being completely separate. But we don't see any of them in nature. And so, in fact, the theory, that same transition that I showed you, predicts that you should have lots of these things. So where are they? And inflation takes care of them because it dilutes it all. The universe got so big that the chance of finding one is infinitesimal. And people do look. There are experiments looking for magnetic monopoles. So inflation is a theory based on a phase transition that happened in the very early universe, a vacuum transition, and a detail that comes out of this, and that was developed a couple of years after, so about 1983, 84, that the transition isn't completely uniform, and there are little fluctuations that develop in that transition. And those are the fluctuations that lead to galaxies and clusters of galaxies today. Okay. And all of this is testable by observations of the microwave background. So here we are again. And we're still stuck here. We're still right around here. We got inflation, and the next thing we have to get through is that there's a little bit of an asymmetry between matter and antimatter. So again, antimatter is probably not something that you go about thinking every day. I do, but that's a different. That's my problem. So we're going to have to say a little bit about what is antimatter and where is it, and what's the role of grand unified theory. So antimatter was proposed again in the 30s or 20s. My history is failing, by Dirac when he tried to make a relativistic theory of quantum mechanics. Basically, he said that, well, we have electrons, but to make the theory work, you have to have another particle called a positron. It's exactly the same as the electron, same mass, all the properties the same, except for the electric charge. Instead of being negative, it's positive. Okay. That was a pretty wild suggestion at the time. And then, of course, this is extremely well known now, and you can produce these easily in the laboratory. You can make accelerators, which have you collide electrons and positrons together. But all the particles have, essentially all the particles have antiparticles. The proton, which is made of 3 quarks, they're called U, U, and D. We don't care about the nomenclature right now. But an antiproton would be of 3 antiquarks. and there are other particles, pions, kaons, etc. All the particles have their antiparticles. And they were observed originally in cosmic ray collisions. So the cosmic rays are particles that come streaming down onto the Earth, onto our atmosphere. They collide with the atmosphere and make new particles, just like we do in accelerators. And these antiparticles were observed there. And as I said, you can readily produce them in accelerators. That's been going on for a long time now. There are also some special particles. They're called force carriers. The photon is the one that you know mostly about. That's the particle of light, and that governs the electromagnetic interaction. But each of the forces that I mentioned has a force carrier. The weak force has 3 of them. They're called W and Z. The strong force has 8 of them. They're called gluons. They have slightly different properties. The gravity has 1, which is called the graviton. And grand unified theory has a bunch more, and they're collectively called X's and Y's. And these things will actually mediate. So what is a baryon? I put that up there. Well, baryons are particles made of 3 quarks. So the proton is a baryon. And these baryons appear to be stable. So there are very few stable particles in nature. There's the electron, and the reason it's stable is because electric charge is conserved. There's never been a process that's ever been seen where the electric charge changes from the initial to the final states. So if electric charge is absolutely preserved, the electron, being the lightest charged particle in nature, can't decay. There's nothing to decay to, because you would have to violate electric charge. If baryon number, so it's like charge, but it's a different kind of charge. If baryon number is conserved, the proton is the lightest baryon, and it can't decay. But in a grand unified theory, baryon number is not conserved, and protons could decay. So before that, we can look at neutron decay, and it's something that's very well known. So neutron is a baryon with 3 quarks. It decays to a proton, electron, and an antineutrino, and that's going through a W particle for the weak force. So this is a weak interaction. Its lifetime can be computed much more accurately than what I have here, but it's about 10 minutes is its lifetime. The proton, so will in principle in a grand unified theory decay into a positron, so the electric charge is conserved, and a quark-antiquark pair called a pion. Now, this X particle that mediates this decay is really heavy. I mean, so heavy that we haven't been able to produce it. So this is an untested theory. There are a lot of tests of it, but it's never been verified yet. But this lifetime is extremely long, about 10 to the 32 years. Okay, red flag should go up in your head. Universe is 10 to the 10 years. How are we looking for particles that are living 10 to the 32 years? Okay, we can think about that for a little while. So we're still chugging along here. We've made, so with that, with protons being able to decay, we can change the baryon number of the universe, and we can get rid of all the antimatter, and we're all made of matter, because you can't put the two together. They would just annihilate, and it sounds very dramatic, but that's what would happen. And so this was very important. And that was also something that was previously ascribed to the anthropic principle, that if you didn't get rid of, if there was antimatter, we wouldn't be around to ask the question, where's the antimatter? So, but once you have a theory that can actually predict the fact that the antimatter goes away, you drop the anthropic argument. So there are more transitions. Not going to go through them. That electroweak going to the weak force and the electromagnetic force happens at about 10 to the minus 10, so that's 1/10 of a nanosecond. And then there's a later one where the quarks eventually find themselves into the baryons and other particles. That happens at about 1/10 of a millisecond. So we just did a little bit of a jump here. So we're moving up on this diagram until we get to nucleosynthesis. So to say a little bit about this, because this was actually the foundations of what Big Bang cosmology is about now. And this was developed in the 40s by George Gamow, who I mentioned a little earlier, Alpher and Herman. So Alpher was a student, Herman his research associate. And they were basically trying to understand the abundances of the light elements. And it was actually Alpher and Herman that found that, this theory predicts that there should be some light in the universe, background light. And Alpher took it to his advisor, Gamow, who immediately got very angry. And he said, who's ever going to discover something at 3 degrees? Stop wasting your time and do something useful. So here's Gamow, Alpher, and Herman. And they, this theory is actually usually ascribed to these 3 people, Alpher and Gamow again, but beta. So you have Alpher, beta, and Gamow. This is not a joke. This is not a joke. If you want, I can tell you a story about this afterwards. Gamow had a great sense of humor. You see, Herman is missing here. Herman, he wanted to change his name to Delta. Didn't happen. So nucleosynthesis is responsible for, this table is only responsible for the hydrogen, helium, and lithium. Beryllium and boron are coming from cosmic rays. Everything else comes from stars. So the theory seemed again to fail. So there's always ups and downs. And so people dropped looking at the Big Bang theory and looked for where the elements come from, and that they come from stars. So stellar nucleosynthesis was a growing field in the 50s, and that's great, and we understand a lot about where the elements come from. But there are still some problems. The amount of helium in the universe is about 25% by mass, and there's no way of getting that from stars. And deuterium, which is heavy hydrogen, you might have heard of heavy water, but then that means that instead of H2O, it's HDO. So deuterium, it's a bound state of a proton and a neutron. That shouldn't exist in nature because it should all get burnt in stars, and yet we see deuterium present, and that could only come from the Big Bang. So with a limited scope, Big Bang nucleosynthesis, Gamow's original theory concentrated on only the lightest of the elements. And so that puts us at around a few minutes here after the Big Bang. And that gets us to the microwave background, which is, I think, the last real topic I'm going to talk about. This is from the paper of Alpher and Herman, you see 1948. And you don't have to worry about the graph. I wanted just to, if I can find it from this angle, somewhere here, it says 5 degrees. Oh, here, 5 degrees. So this was their prediction. They did some calculations. They said, the universe should be filled with radiation at about 5 degrees. They actually did better than that because they said, well, we don't know everything that well. It could be as low as 1 degree. So they're saying in 1948, the universe should be filled with radiation with a temperature between 1 and 5 degrees. And then in 1964, Penzias and Wilson were developing a radio antenna to track a satellite, a communication satellite, and they had noise in it. And everything they did, they could get rid of the noise. That noise can be interpreted as a temperature. It's called an antenna temperature at 3.5 degrees. Okay. They weren't aware of the work on cosmology by Gamow and his collaborators, or Alpher and Herman, but this was at Bell Labs, and down the street is Princeton, and the people at Princeton knew very well what Gamow had predicted. And they said, you guys just discovered the Big Bang. And that happened to be the case. And it's been measured increasingly better as time goes on. This is the Kobe satellite, which was launched in about 1990. And this is what it measured. This is called the black body spectrum. So this is, you see the level of accuracy, it's 2.7255 is the temperature of the universe. This curve is not just a curve drawn through the boxes of their data. That's a theoretical curve. It's based on one number, the temperature. And if you're any physics undergraduate student should be able to reproduce that given that temperature. The boxes here, this is actually, if you turn this into your lab, you'd probably get yelled at because this should never happen. Probably means that their boxes are too big, that is, they've overestimated their errors, that they really measured it much more accurately than is shown here. And as time went on, so this is what Penzias and Wilson saw, a uniform temperature of about 3 degrees. Kobe satellite started seeing now, not only that, here you see the galaxy again, but they saw a fluctuation. So that was the first time the fluctuations in the microwave background. And these, everybody knew they had to be there, but they're so small, the level of 1 part in 100,000, that they were very, very hard to measure. You need to have a thermometer that can measure microkelvin, essentially. So very, very hard to make this kind of measurement. And then some 10 years later, the MAP, or now called WMAP for Wilkinson satellite, measured it into much, much, much finer detail, much higher resolution. And then you get to the Planck satellite, which was launched about 15 years ago. And this is what they see today. And so this is that same map, that same disk that I showed you very early on. And here again, this is the spectrum. This is different distance scales. You don't have to worry about really what L is. Small distances, that small angular distances are on the right. Large distances are on the left. The data gets a little bit sloppy at the left because there's not so much data you can take at large distances. But at small distances, you can take lots of data. And this curve again is not a line drawn through their points. This is a theoretical curve now based on 6 parameters, only 6. And the detail at which this fits, their observations fits the theory is, to me, is absolutely remarkable. So the implications of coming from Planck, from the Planck satellite, is basically a confirmation, in some sense, a confirmation of inflation. It doesn't prove inflation, but it means that the predictions of inflation, which I didn't go through that, but it did predict quantitatively what those fluctuations, what kind of spectrum of fluctuations you would have coming from that phase transition, that vacuum phase transition, and those are showing up in the microwave background. It also tells us something about the composition of the universe, how much ordinary matter there is, how much dark matter there is, and how much dark energy there is. And so here's a little pie chart. It's simple to understand that most of the energy in the universe seems to be this dark energy, which could be a cosmological constant. It's sort of unsatisfying that we don't know what 68% of the universe is made of. And there's another quarter of the universe, which is dark matter. We also don't know what that's made of. All we know is this 5%, which is what we're made of. So there's a lot of questions. I mean, it's nice we have this detail, but we still, there's a lot of questions that are unanswered. This dark energy could, as I said, could be the cosmological constant, and this goes back to Einstein. He considered it his biggest blunder, but it could have been, again, as I said, another stroke of genius, because that cosmological constant might actually be there. The problem is that it's so tiny. In dimensionless units, it's a number like 10 to the minus 121, which is a ridiculous number. There are no numbers like that really in physics. So, but this proposition by Einstein is just another one of his propositions that so unbelievable. So now we're past the microwave background and we're getting towards today. And so now what? Well, you went through the dark ages. You went through you got neutral matter. Those density fluctuations grew to galaxies, dwarf galaxies, eventually clusters of galaxies, and you had the first stars. And where is it going? Well, we're going into this period of accelerated expansion. And you can see that a little bit here. It's starting to speed up. It's not a line anymore. And eventually the universe will dilute itself. Eventually we'll go into this phase where the universe is expanding exponentially again. And we will not see any more of the universe. In that case, what we see is what we have. But that'll be a long time, so you can go home safely tonight. And so I'll stop there.
Thank you very much. We'll take some questions, and then I have an announcement about a special event coming up. So, questions? Yes.
One of the slides said that gravity was strong at the very beginning, which to me makes a lot of sense. But it seems like some of the redshift that we see should be gravitational redshift then, or what do you think?
As opposed, so
Well, are they saying it's all Doppler redshift?
yeah, it's what we see when we see that the galaxies are receding from us. That's coming from the fact that they're moving.
None of that redshift is gravitational redshift?
No, that the dominant, there will be some due to that from coming out of the gravitational well, but you're really seeing these things moving away from you at those speeds that it is really just the Doppler effect.
Are you secretly Einstein?
Am I what?
Secretly Einstein.
No.
Well, it's not a secret now.
No comparisons to be made there. Einstein was truly a genius. He only got one Nobel Prize.
Yeah.
You can count pretty easily if you know physics. There should have been at least 6 of them.
Is it that the earliest event or the earliest phenomenon we can observe is the microwave background, and the rest of this is modeling that then predicts what we see in the microwave background?
Yes and no. So if we're talking about the earliest thing that we could see directly, that is by observation, say through electromagnetic interactions, yeah, the answer is yes. Because before the microwave background, this 300,000 years, so that disk in that first slide, the light would scatter so much that it doesn't, it keeps getting scattered before it comes to us. And it's only at 300,000 years do we get that it's, how do we get this?
Sorry.
Let me just finish the, how do we, that's off.
You can project. Just
Oh, okay. That's maybe.
Give them up.
Let me see how I can do it this way. The information that we get, when you say it's just modeling, it is somewhat more than modeling because, I mean, everything is modeling to some extent, but there are definite predictions that we see, that we make about what happens very early on. And they predict features. So they're not observations by counting photons, but they are those bumps and wiggles in that plot that I showed. Those are things that are predicted. And so in the sense that by observing those bumps and wiggles, you are observing what happened very early on. And same thing with the light elements, that you're making predictions for the abundances. When you make a calculation, you say there's 24% helium in the universe, and then you go out and measure it. So you are in some sense measuring what happened very early on. Now, there is a way to make a direct measurement at some point in the future. I'm sure it'll happen, might not be in my lifetime, and that's coming from looking at neutrinos. So neutrinos, there's a background of neutrinos like the background of photons that we're seeing, but those were emitted again back when the universe was about 10 to the 9 degrees. So after just a few minutes. And so those neutrinos, I mean, they're very hard to measure. Neutrinos are anyway hard to measure, but these are very low energy ones. So once those neutrinos are measured, then we will have a direct observational measurement to that period of time. And people are trying to figure out how to do that.
So, was there actually a bang during the Big Bang?
Okay. So if you have to now, if you talk about the Big Bang theory and just the way we normally think of it, so there was a time t equals to 0. Yeah, it was probably a pretty big bang. Yeah. The thing that you have to be careful about is that it wasn't localized, right? So it's not like, you know, you can go out in space and say, oh, this is where it happened, right? No, because there wasn't anything like that. It happened everywhere, right? So the Big Bang not only created all the matter and energy, it also created the space and the time as well. So it happened everywhere all at once. So that's a pretty big bang. We don't necessarily think about it that way anymore because, especially with inflation, the universe might have always existed. And one of these phase transitions might have happened. And from that, what we call the Big Bang was just a transition in something that's always out. I mean, we're talking about distances now that are just absolutely ridiculous. I mean, we don't get signals from them. We will never get signals from them. So it sort of leaves the realm of physics and goes into philosophy or metaphysics. But that is a way of thinking about it.
You said that over here.
Oh.
You were talking about Einstein, the cosmological constant, and how that turned out to be wrong, and he was embarrassed. But then maybe he wasn't wrong, and maybe because of the expansion of the universe. But the reason that Einstein proposed the cosmological constant and the current expansion of the universe are two very different things, aren't they?
Absolutely.
And so to give him credit, I don't want to throw shade on Albert Einstein, but to give him credit for, hey, he may have been right, but the reasons were very different. Is that correct, or am I misunderstanding that?
Well, where he's right is that he introduced the constant into his equations. They're called Einstein's equations. The original set of them didn't have that constant, and he found that you could add that constant. In fact, you sort of have to add the constant, but nobody was thinking about it in those terms. So you're right, he didn't predict the accelerated expansion of the universe today. There would have been no way for him to think about it in those terms. But the fact that the constant is present, and he predicted the possibility of this constant, that's all.
Or you could say that that is a mark of a true genius, in that even when they're wrong, they get the right answer. Thank you very much. Let me now, let's see if which one is, oh, there? Yeah, I think you're right. Thank you. Okay. So this concludes our summer of Astounding Astrophysics. Thank you. We want to take a little time and rest up as we prepare for the autumn of Astounding Astrophysics. Now, we don't have a entire series of talks by professors here at the University of Minnesota. We're going to have one very special talk by someone not at Minnesota. We heard a talk by Michael Coughlin about gravitational waves, ripples in space-time, detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. October 29th, Wednesday, 7 p.m., in a room bigger than this, we're going to have a public talk by Professor Kip Thorne, who got the Nobel Prize for LIGO and gravitational waves. This is part of the Fine Theoretical Physics Institute's Meisel Lecture series, and you're all invited. How many people are interested in? Yeah, yeah, we're going to need a bigger boat. This should be a lot of fun. We're not actually, we tried to get the title before I could make this announcement, and we haven't heard it yet. So we're not sure what he's going to actually talk about, because he could talk about Hollywood. If you've seen the movie Interstellar by Christopher Nolan, he was the science guy that provided all that science for that movie. And it was based on his understanding of black hole dynamics. So maybe he'll talk about that. But I'm sure whatever he talks about, it'll be fascinating. If you would like to keep up to date on future public talks, which we have throughout the year. There's a mailing list that you can register. There's a little QR code on any of the posters or other things. And we will also, through that mailing list, we're going to send you a survey. I know, a survey, right? I got a haircut. And as soon as I left, I got a survey. How was your haircut? And it was like, well, I went in to get my haircut and you cut my hair. And I left a tip. I thought that was the survey. But we would like to know, this was an experiment, right? And you all have made it an astounding success. We weren't sure if we built it that they would come, and you did, and we're thrilled by it. So we'd like to know, again, more? Would you more astrophysics, the quantum realm, nanotechnology, the material world, particle physics, Higgs boson? Let us know what you would like us to do and talk about. This, I have to thank a series of people for making this all possible. First, of course, the speakers, Lucy Fortson, Michael Coughlin, Lindsay Gleesner, Patrick Kelly, and why is it, there, he's off. I also want to thank the Communications and Marketing Office of the College of Science and Engineering, who helped us publicize this and get the word out to everyone. And so I want to thank Rhonda Zern, Kaylee Pluchner, Ellen Poof, and Megan Orr. And most importantly, I want to thank the astounding staff here at the School of Physics and Astronomy, particularly Sean Albertson, Valerie Birch, Greg Bacco, and Emma DeBruyne. Greg and Sean have been here every Tuesday. They've been here before the first person arrives, and you've been getting here earlier and earlier. And they're here at the end to set up the overflow rooms. This was a work in progress about the technology. We've been recording these talks, and we have some work to do editing them, but they will be posted. And if you subscribe to the mailing list, you'll get the links. You'll get notice when these things get posted. And the important thing is, this has all been a volunteer effort. Greg, Sean, Valerie, Emma, they're not supposed to be here. not here, not now, not tonight. This is not, they have a day job. And I know because I'm the head of the school and I know what their day jobs are. But when I proposed this idea, everyone was on board for it. Everyone, the speakers, all the staff have volunteered their time and effort and expertise to make this all possible. And it's been very rewarding to see the turnout week after week and see the interest. And for final words, you know, this work has all that we've seen presented here. It's been supported by the National Science Foundation, NASA, the Department of Energy. And as a final word, I was thinking, I looked at NASA's official model. They have a motto for this funding agency. And their official motto is for the benefit of all, which I think sums up very nicely what we've been trying to do. But then I looked a little deeper and I found out they have an unofficial motto. And I like that one even a bit better. It's ad astra per aspera, which translates through adversity to the stars. Thank you, everyone, for joining us.